Today, I'm going to talk about constraining 3D fields for better 3D reconstruction and view synthesis. Recently, there has been a revolution in 3D vision and graphics through neural shape and appearance representations, as we all know. For example, in the case of 3D shape representations, the key idea is to not represent the 3D shape explicitly, but instead to consider the surface implicitly as a decision boundary of a nonlinear classifier. It's illustrated here on the right, where we have the decision boundary between the red and the blue points representing the surface. Mathematically, this can be formalized as a mapping with parameters theta, typically represented by a neural network, that maps from a 3D coordinate to a occupancy probability, for example. There's different variants of this model. For example, you can also, instead of outputting an occupancy probability, output a signed distance field that has been done by Park et al. Or you can model the color and the density of every 3D point based on the view direction, and then composite this together into an RGB pixel value in order to render an image, as done by NeRF. And the NeRF results are quite amazing, as we all know them. So they can reconstruct the appearance from novel views quite precisely, even if the geometry is complex. And they also work with complex illumination conditions, such as these reflections here. However, in NeRF, many input images are assumed to be given, like illustrated here for the drum scene, for example. You need all these images here. But in the real world, we often are not in this lucky situation, but maybe we just have 3 or 5 views of the input. So we have to deal with sparse inputs, as illustrated here. However, if we apply vanilla NeRF, for example, a state-of-the-art MIP-NeRF model here, to such a free input view scenario, we get a lot of floating artifacts, as you can see here. And basically just the original 3 input views are reconstructed well. But if I want to synthesize a novel view from another viewpoint, this doesn't work very well. And you can see that the depth is also very noisy, and there's a lot of floating artifacts here. But what we want, of course, is a result as the one here on the right, where we have a nice reconstruction with a relatively clean and accurate geometry. So what's causing this problem, actually? Well, the cause for this problem is the shape appearance ambiguity, which tells us there exists an infinite number of photoconsistent explanations for input images in areas of similar color. So for example, here we have a region of similar color that is observed by 2 cameras. And while this surface here as star is one possible solution, there's infinitely many surfaces that are also solutions that are photoconsistent. So how can we scale NeRF-like models to these sparse input scenarios? Well, of course, the answer is through regularization. And I want to present 3 different regularization approaches that we have been trying out in our lab over the last couple of months. The first is RegNeRF, regularizing neural radiance fields. The second is MonoSDF, a NeRF paper this year, exploring monocular geometric cues. And the final one is TensorRF, a model for tensorial radiance fields, a new tensorial radiance representation that leads to useful inductive biases through its architecture. But let's start with RegNeRF. And it's joint work with Michael, John, Ben, Mehdi, and Noha. Let me first present a high-level overview of RegNeRF. Let's consider this scene here on the left with these 3 objects. We can project this scene into the input views for which we have observations, and then minimize a reconstruction error by backpropagating gradients to this 3D representation. In the case of a NeRF, it's a multi-layer perceptron to optimize the parameters of this multi-layer perceptron in order such that the reconstructed images correspond as much as they can with the observations. But what we can also do is we can project this scene into arbitrary unobserved views for which we don't have an input observation, right? We can also render arbitrary unobserved views. How do we do this? Well, for any random patch in any random view, we define for every pixel a ray. and then we traverse that ray, and for each point, each 3D point that's sampled along the ray, we pass that 3D coordinate as well as the viewing direction into an MLP, and we retrieve the color and the density from the MLP. And this is then alpha composite together using standard neural rendering, standard volumetric rendering, into and yields a color value and a expected or estimated depth value for that particular pixel. And we do this for all the pixels inside these random patches that we have sampled from the random viewpoints. Now we have rendered random patches, and we have rendered them both in terms of color and in terms of their depth, and we can try to regularize those. So let's start with the color regularization. What we do for the color is we train a model on the manifold of all natural image patches. So we have a very big data set, and we train a real NVP, which is a normalizing flow model, on all of these image patches from that data set to yield a model that gives us the probability of any possible input RGB patch, right? So because we use a normalizing flow model, we have access to the log likelihood, so we can define the loss function as the negative log likelihood of that real NVP model. So in other words, we're trying to generate patches from random viewpoints that look like natural patches that are observed in random images. For the geometry, we use a relatively simple regularizer. We just render these depth patches, and then we use a standard variational loss. In practice, what we do is we minimize the L2 distance between neighboring pixels in terms of their depth in order to yield smooth surfaces. So these are the two regularizers that we apply to help NeRF find the solution. But what we also found, what is important, is to use what we call scene space annealing. If we naively sample points along the entire array for these sparse scenarios, we find that this leads to degenerate solutions. And we can avoid this using scene space annealing over the first iterations, where we sample points more closely to the expected scene center by adjusting the near and the far sampling planes, here shown in green and in orange, such that we sample only between these. And then during the course of optimization, we push this near and the far plane further away from the scene center, so that we sample also points outside that scene center. And this significantly helps in avoiding these degenerate solutions, because we start with something that is already like reasonable in its center, and then we build up the reconstruction from there. So this helps the optimizer. So in summary, we have key three ideas in RegNeRF. The first is to regularize geometry and appearance prediction of unseen viewpoints. And then we have the scene space annealing technique I just described. So here are the results. This is the result that we have already seen. On the left, you can see the MIPNeRF results, and MIPNeRF is actually the basis for our model here. So the only difference is that we add these two regularizers and that we add scene space annealing, and we get to those results shown on the right. So this is a scene from the forward-facing dataset with just 3 input images used here. Here's another example where we compare again to the MIPNeRF baseline, where you can see much more floating artifacts, which are largely eliminated on the right-hand side. Oops. And finally, another example where you can see that the MIPNeRF model sometimes reconstructs the object multiple times because it tries to fit the input views, but this doesn't lead to a consistent 3D reconstruction. While in our case here on the right, with the regularization, we obtain a single 3D model in the end. Let's look at some ablation study here now. What we plot here is the performance in terms of PSNR with respect to the number of input views, and maybe unsurprisingly, we observe a larger gain in performance for a smaller number of input views with respect to the baseline. But still, even for higher views, we have small gains, or at least we're not worse than the baseline. What we can also see is that with just 3 input views, we obtain a PSNR that's similar to the PSNR obtained by the baseline with roughly 6 to 7 input views. So we can significantly reduce the number of input views for reconstruction. Here's another ablation where we have our reconstruction here in the second to the last column, and we remove some of the components of our model, and we can see that if we remove the appearance regularizer, the reconstruction works still somewhat okay. It degrades a little bit, but if we remove the geometry regularizer or scene space annealing, then the reconstruction breaks apart. So these two are definitely the most important components of our model, but the appearance regularizer also helps a little bit. Let me now move to MonoSDF. And this is joint work with Chihao, Songyu, Michael, and Thorsten. Well, so far we have focused in RegNeRF on the novel view synthesis problem. Of course, also 3D reconstruction is an ill-posed problem and suffers in the presence of little views or textureless regions. And this is illustrated here, where in the top row you can see the results of VolSDF, which is a state-of-the-art implicit neural reconstruction model. And you can see how these are inaccurate on DTU for 3 input views, and on larger scenes also for more input views. Like, of course, for larger scenes you need more views. And at the bottom you can see the results that we'd like to achieve using our method. So the question that we wonder about here is, well, can we actually exploit complementary recognition cues to overcome the reconstruction ambiguities, right? If we reconstruct just using a NeRF or a VolSDF model, then we use reconstruction cues, we use matching cues, but can we also use recognition cues? Now, what do I mean by recognition cues? Well, here's an example where we predict from a single image a geometric cues, in this case the depth, but it could also be normals, and this is from one of the earliest works, seminal work from Eigen et al. In NIPS 2014, depth map prediction from a single image. While these results were still at a level that they would not be useful for 3D reconstruction, the field has matured significantly, and results look like this today. These are results from Sameh et al. On the OmniData model and dataset, which is a model that constructs large supervised datasets from 3D scans. And you can see that with better compute and larger models and more advanced models, and in particular larger datasets, you can get much better single view geometry than before. So this motivated us to revisit this idea of using these recognition cues for this problem. So here's an overview of the OmniData vision pipeline. What it does is basically produces a 3D reconstruction or uses a 3D reconstruction that exists coming from a data set like Matterport or another data set. And it then samples viewpoints randomly inside that 3D space and produces the ground truth automatically. And that's the training data for the model. And this leads to very, very generalizable models. And so we use this model out of the box for our data sets. So here's an overview of our pipeline for MonoSDF. This is seen from the Replica dataset. This is an input view. We shoot a ray like a NeRF. We sample points along the ray. And then we have a neural implicit scene representation. And we try different scene representations in our paper. So we have the classical MLP representation like in VolSDF. But we do have also feature grid-based representations, both single resolution feature grids, but also multi-resolution feature grids like in instance NGP. So the input point is then passed through either the MLP to give the assigned distance value, or it's used as a query inside this multi-resolution feature grid, and then the resulting feature is input to a little MLP that outputs the assigned distance value, and then we have another one that's not illustrated here that outputs the color. The assigned distance then goes through a transformation like in VolSDF to produce the density, and then together with the color we can then, like for each of these points, we have the color and the density, we can then alpha composite the image together and render this, and then we can use a reconstruction loss. But what we do now in addition to this is we render also the depth map and the normal map. And we compare those renderings to the predictions of the OmniData model on the original input image using a depth loss and a normal loss. while normal loss is a pretty standard loss that compares the difference between the directions of the predicted and the estimated normals, the depth loss takes into account also that estimating depth from a single image is actually ambiguous. The scale and the shift cannot be estimated precisely, and hence we on the fly also fit the linear parameters of the depth map to make the depth map align with, or the estimated depth map align with the predicted depth map. So let's look at some results. So these are results including depth and normal cues. And this is what happens if we remove the depth and normal cues. This is what happens if we use only the depth cues, and finally with the depth and the normal cues again. And this is the ground truth map. Here's an ablation study on the Replica dataset. We show results for the vanilla MLP and the instance NGP-like feature grid representations here. What we can see is that in both cases, both for the MLP and for the multi-resolution grid, we get the best performance if we use both cues, both the depth and the normal cues, for we found the normal cues to be slightly more important. What we also found is that these monocular cues can significantly improve convergence speed, and this is illustrated here on the right, where you see the number of iterations on the x-axis and the f-score on the y-axis. And you can see that, for example, in the case of the MLP, the performance, the model converges much faster to a much better value if you use these monocular cues as well. And the same holds true also for the feature grid. The feature grids converge slightly faster than the MLP, but in particular for this replica data set, we found that the MLP in the end yields the best accuracy. So here's some qualitative results on this ablation study on the replica dataset, where you can see that, well, if we use the MLP alone, for example, and adding the depth cues to that, we get better overall structure, but adding the normals on top of the depth cues, we get also fine details, and some of this noise in the background, for example, here at the wall, gets removed. And so this result is actually very close to the ground truth for this particular dataset. Here's an ablation study in ScanNet, where we can see that for these datasets, because they have so little texture, ColMap and VolSDF without the cues fail almost entirely. And Manhattan SDF is concurrent work to ours that uses Manhattan world priors, which leads to better results, but is still like less accurate and less detailed as our reconstructions here. What we found on the DTU dataset is that for the few shot scenario with just 3 views, the MLP in combination with the monocular cues leads to the overall best results. While if we use all of the input views, then we get the best results also using the cues, but with the feature grid representation. And we believe this is the case because the MLP has an inductive bias, a useful inductive bias that helps in the few shot case, in addition to these monocular cues that we provide. So here's some more results, in this case on the ScanNet dataset. Okay, let me continue. These are results on the tanks and temples dataset, which is containing very large scale scenes that are very hard to reconstruct. I think we are one of the first methods that actually attempted to reconstruct or succeeded in reconstruct indoor scenes at that scale with implicit reconstruction methods. And here are results on the free view setting on DTU, where our method is able to reconstruct, while if we remove these monocular cues, or we just use ColMap, we get much less detailed reconstructions. And finally, what we also did is we applied our technique to inputs of much higher resolution. The original OmniData model has a comparably small resolution, and this of course also reflects on the final reconstruction accuracy. But what we can do is we can reconstruct multiple different patches of the input images separately and then unify them, and this gives us overall even better reconstruction, as we can see here. So this is quite preliminary, and we added this to the supplementary. Now, let me, in the last few minutes, come to the final project I'd like to share with you today, which is TensorF. And this is joint work with Anpei, Zhejian, Jingyi, and Hao. The goal in TensorF is now back to Radiance fields and novel view synthesis to obtain photorealistic, fast, compact, and simple 3D representations for view synthesis. Simple means we can implement them using vanilla PyTorch without any specialized or customized kernels, like in Planoxels or Instance NGP. The idea of TensorF is to decompose the scene not into just voxels or to represent it just with a multi-layer perceptron, but to decompose it into matrices and vector products. And this is illustrated here, for example, for the vector matrix outer product representation, where we have 3 different components. Like we represent this plane here with a matrix, and then the other component here with a vector. And then we have this for the other 2 cases as well. And then we have many, many of those components that we all sum together to yield the final representation. And then we use interpolation to query the corresponding values inside these this representation in order to obtain the RGB and the density value. Let's look at this model in a little bit more detail. This radiance field, how we model it, corresponds to a dense 3D voxel grid with per voxel features, but we decompose that voxel grid into these tensor components. So each voxel contains the volume density and an appearance feature vector that we want to query. This is illustrated here. So we have the volume density. This is a scalar, but we have an entire vector, which is the appearance feature vector that goes into a model that jointly with the viewing direction predicts the RGB color. We can use different types of models here. For example, we can use an MLP or just spherical harmonics. Our model works with both. For the decomposition, we experimented with the very simple CANDECOMP PARAFAC decomposition, which is basically just a decomposition into vector products. And we also proposed a new vector matrix decomposition that gives a slightly higher performance. And there's a trade-off between these two that I'm going to talk about next. It is a 4D representation because there's 3 dimensions for the spatial arrangement here, so 3 spatial dimensions, but there's this 4th dimension, which is the feature mode dimension that we also have to represent. As a little remark on the following slide, this feature mode is not explicitly shown because it's hard to draw in 4D. We only show the 3 spatial dimensions, but the 4th dimension is always present in our representation, and that's why it's a 4D tensor that we represent. So here's an illustration that compares the CP decomposition and the vector matrix decomposition side by side. For the CP decomposition, we just have the vector product. So each of these components is a product of 3 vectors. It's very lightweight, but we need many components to represent the scene. At the bottom, we have the vector matrix decomposition, where we decompose into vector and matrix products. This is more expressive, so we need less components, but each of the components itself requires more capacity. Using our model, when plotting the 3 dimensions training time, model size, and quality, which is the size of this little circle here, we observe that our model runs comparably fast while achieving still good results at a small and compact model size. So here are some results. Now you can see how the training, the results emerge during the training process. So what we observe is that using only 7,000 iterations, we obtain better results than vanilla NeRF at 500,000 iterations, while not requiring any CUDA kernels, just using a vanilla PyTorch implementation, unlike other techniques like Planoxels, for example. So here's the result after 7,000 steps, which are produced on a single GPU in 3 minutes and 24 seconds compared to 35 hours of NeRF. So we have even better PSNR than NeRF that requires 35 hours. And if we train further, if we train for 8 minutes, then we have further increased the PSNR here, while it's being still faster than NeRF. As already discussed, we have these two different decomposition techniques, and each of them has their own advantages and disadvantages. So let's look first at the CP decomposition technique. For the CP decomposition technique, we obtain very compact models, so even smaller, 3.7 megabytes compared to 5, than MLP-based representations in vanilla NeRF, which are known for their small model size. So we get a higher quality at a smaller model size, but require many of these vector components. So so training time is a little bit slower than the other representation, but still much faster than NeRF. In contrast, the VM decomposition requires more parameters per component, but in contrast then requires less components. And so we have faster reconstruction and ultimately higher rendering quality at the expense of a less compact representation. So here's a result of the VM decomposition. On the left, we can see the CP, on the right, the VM. We can see that it requires less components, but it requires more space, in this case 70 megabytes, while, for example, the vanilla NeRF representation requires only 5 megabytes. Another feat of the VM decomposition that we observed is that through its matrix vector products, it preserves high frequency details better than the other representation. As you can see, for example, here for the chair. Now, let me summarize. Today I presented RegNeRF that showed that regularization of unseen views significantly boosts sparse novel view synthesis. I've demonstrated MonoSDF, which demonstrated that recognition queues can complement matching queues for 3D reconstruction. And finally, TensorRF, which is a novel tensorial representation for Radiance fields that is fast, compact, accurate, and easy to implement. And I also like to highlight that the code of all of our models is available, so we invite you to try it out if you like.